Welcome to this presentation. My name is Francisco Caetano. I'm a PhD candidate at the Eindhoven University of Technology, and I will guide you through our work that was accepted at ICCV, DisCoPatch, our solution to improve and speed up out-of-distribution detection for images. Distribution is essentially an acceptable range of semantic, covariate, and domain shift. When we encounter an additional covariate shift like this blurry horse, then we are out of the distribution. When we encounter a novel class like this bagpipe, we are out of distribution. When we represent a known concept in a different way, like a sketch of an airplane, we are out of distribution as well. It has been observed that in adversarial setups, in which the discriminator is trained with batch normalization, that clean and adversarial samples actually have different statistics. They correspond to different distributions. So our approach takes this idea and uses it to delineate the in-distribution boundary. First, we need to make sure that we can trust the batch statistics, and we do that by patching the images. During training, we actually normalized all the patches together so that we can have more robust features, but during inference, we could be mixing in-distribution patches with out-of-distribution patches, so we just normalize them on a per-image basis. The first element of our framework is a variational autoencoder that we train in a standard way to learn how to reconstruct and sample patches from the training distribution. We then train the discriminator to be able to distinguish from both reconstructed and sampled patches and the ground truth in distribution patches. We do this because the reconstructed patches will have low frequency content, while the sampled patches will be more prone to adversarial artifacts that are typically high frequency. This will help us to build a more robust in-distribution boundary. The adversarial loss will keep encouraging both the sampled and reconstructed patches to look more realistic. During inference, we can rely solely on the discriminator that has already learned that boundary between the distribution that we use for training and all other kinds of images and corruptions. This discriminator then produces an anomaly score that we use to classify each image as in distribution or out of distribution. To validate our model, we evaluated it on the OpenOOD benchmark, more specifically in the ImageNet 1K benchmark. This has several near OOD datasets, far OOD datasets, but also covariate shift datasets. We pitched it against 6 state-of-the-art OOD detection models as baselines. Results we achieved are quite interesting. One of our main focuses was on reducing the latency because these OOD models can be very large and very heavy to run. And we actually managed to achieve big increases in near OOD detection and on covariate shift detection. Although we lag slightly behind on far OOD detection, we are quite close to the level of performance of the bigger models with a 20 times lower latency and using a discriminator that's just 25 megabytes in size. In conclusion, DisCoPatch is an unsupervised, compact OOD detector. It achieves state-of-the-art results on near OOD and covariate shift detection, and it's real-time and resource light. Thank you for your interest in our work and for watching this video. You can scan the QR code to actually access our project page and to have access to our contact details if you have any further questions.